And they're on orbits that are generally much closer to their stars than the terrestrial planets are to the sun. So their years are typically measured in days, or 10 days, or 50 days, much shorter than the 365 days that it takes Earth to go around the sun. So this illustration shows a selection of super-Earth systems with the solar system at the bottom for comparison. You can see they're much closer into their stars, and they're often in systems with many planets. Now, our goal here is to build a model that it can explain how these planets ratio of how long it takes different planets to go around. So in 2-to-1 resonance, the outer planet goes around its star one time for every 2 times the inner one goes around, and then they realign. 3-to-2 resonance is the same idea. The outer planet goes around twice for every 3 times the inner planet goes around, and then they realign. So if half of all super-Earths, just as an example, were in 3-to-2 and half were in 2-to-1, instead of that smooth period ratio distribution, you'd have this staircase kind of function instead. Another constraint is the multiplicity distribution of super-Earths. This is just the distribution of how many super-Earths you see around a given star. And so this is the distribution we see. It's peaked at 1, meaning that most super-Earths are found in systems with just one super-Earth. And what's interesting to ask yourself is, does that mean that most super-Earths are alone, really alone? Or is it just that we miss other super-Earths in those systems, and they really all generally come in systems with many planets? The first model you might think of is that maybe those super-Earths just form where they are. That's called in situ accretion, and it is a model that does not work. And there's a whole other video of the MOJO project dedicated to explaining why that is, so I'm going to leave that there for now. The MOJO project's contribution here has been to show that the super-Earth's orbital configurations are consistent with those planets having formed farther from their stars and migrated inward. And I'll explain that in more detail. So as we heard in part 1 of the series, planet migration we think is a very common process. Anytime a large planet forms fast, while there's still a lot of gas in the disk, it interacts with the disk and it generally has its orbit shrunk. So in other words, it migrates inward. And you might ask yourself, well, can planets just form, and migrate and just fall onto their stars? And the answer to that is no, they can't, because disks have inner edges, and those inner edges act as migration traps. So a planet that forms farther out and migrates inward will stop its migration when it reaches the inner edge. It can't fall onto the star. So with these ingredients, we can build a simple model for how migration can produce the systems of super-Earths that we see. So in this cartoon diagram, the vertical axis is the mass of a planet, and the horizontal axis is its orbital distribution. And this model is called the breaking the chains model for reasons that you'll see in a sec. So starting from a smooth distribution of planetesimals, planetary embryos grow. And they're larger past the snow line, basically resembling the solar system's great dichotomy, because they can grow much faster and larger past the snow line. They grow fast enough, in fact, that they migrate. And so these large embryos from farther out migrate inward, and they end up in chains of orbital resonances. So the innermost planet here is at the inner edge of the disk, holding back the other ones. And the other ones migrate inward, and each time one migrates inward, it gets trapped in resonance with the ones interior to it. And they end up in a long chain of resonances where each pair of neighboring planets is in orbital resonance. So this configuration was driven by the gas in the disk, and it's also kind of held in place and stabilized by the gas. But the gas doesn't last forever. After a few million years, the gas dissipates, and that tends to break these chains. And what does that do? It leads to this late phase of collisions between planets. and the final configuration is much wider and not resonant anymore. Going back to the period ratio distribution, the observed distribution of super-Earths is that gray curve. The red curve shows that staircase-like function. Those are the resonant chains that form in pretty much all systems, but most of them go unstable and produce that blue curve. And basically by mixing the blue and red curve, we can easily match the observations if only 5 to 10% of those resonant chains remain stable, and the vast majority become unstable. Of course, a few percent do remain stable, and we see some of those. Some of the most interesting systems we see, such as the TRAPPIST-1 system, are found in long resonant chains. The TRAPPIST-1 system is exceptional in that it has 7 planets, all roughly the size of the Earth, in a very long resonant chain. And that same mixture of 5 to 10% stable resonant chains, 90 to 95% unstable ones, can also match the multiplicity distribution that we saw before. And what's interesting about that is our simulations indicate that those systems, even with one super-Earth found, should actually have many other planets that are hidden, that are just hard to find. And so we think that this, the fact that there's a lot of super-Earths found with only one super-Earth around a given star, just is because they're hard to find its neighbors. It doesn't mean that they're not there. Finally, we think that the same type of evolution, this breaking the chains style evolution, is really quite ubiquitous. So in this cartoon, on the left, you can see a simple description of the breaking the chains model for super-Earths that we just talked about. And on the right, it's a similar evolution of giant planets. And we think that giant planets follow the same qualitative behavior. They grow big while the gas is still there. They migrate, they form chains of orbital resonances, and when the gas goes away, they go unstable. The main difference between the giant planets and super-Earths is giant planets, when they go unstable, they don't bash into each other usually. They undergo phases of scattering, where one planet usually ends up getting ejected entirely from the system, and the surviving planets tend to have eccentric orbits, just like the giant exoplanets that we see. And in fact, we think that the same type of behavior happened in our own solar system. We think that our own giant planets once formed a resonant chain, and that they actually underwent a late instability also. A relatively gentle instability compared to some exoplanet systems, but an instability nonetheless.
Mojo.